Thank you, happy to be here. So you talked a lot about alien life. I'm kind of alien because I'm not from the field, so that's me. I'm going to talk not about artificial life, like you said, Muriel, but about robotics and AI. So I won't talk about life, but maybe a bit more about intelligence. So I know you're not from the field, so I'll try to give an overview, really, of a field that is pretty huge and pretty multidisciplinary. So where do I come from? I come from, like Hervé said, from SoftBank Robotics, which was formerly called Alban, which is a French company, which was a French company, bought by a Japanese company called SoftBank Robotics. And we are the worldwide leader in humanoid robots. So you see here on the right three products that we build. On the left you see Now, which is a small companion robot. On the right you see Pepper, which is 1.20 meters. And in the middle you see Romeo, which is a more research platform, so we don't sell it. Now you can buy it if you want. You can find it in hospitals, in schools, in research labs. And Pepper, you can buy it if you're Japanese and if you live in Japan. Soon if you're Chinese and you live in China, but not yet in Europe. And Romeo, we don't sell it yet, but the goal is in the future to have a Romeo help elderly people at home. All right, so robotics. I guess you all know more or less what a robot is. You've seen many in movies, in books, maybe in the news recently. They are often evil. They are sometimes nice. Well, today I will try to demystify a bit the buzz around robotics and artificial intelligence. And hopefully you will know more at the end of the presentation. So I will have mainly three sections. I have a lot to say, maybe too many slides, so maybe I will skip some of them. First I will start with a little bit of historical perspective on where robots come from, how to build a robot, and then more into, well, what's currently the limits of the state of the art and what is really the research today in robotics. So let's start with a little bit of history. So first, what's a robot? You see a definition there. A robot is a machine capable of carrying out complex series of actions automatically. That's pretty vague. And actually, well, basically the only difference between a robot and a machine is the word complex. Is there a pointer? Yeah, is the word complex that you can see here. That is pretty subjective. So of course, I guess everybody would say that this robot, which is called Atlas by Boston Dynamics, is a robot, clearly. This, most people would say it's also a robot. You would find that in factories. Washing machine, depends if you think this is complex or not. But I mean, according to this definition, everything fits. So the point here is to show that, well, it's not a difference of nature between machines and robots. It's more a question of degree. But what about the word robot itself? Maybe some of you know where it comes from. It comes from a play by the Capek brothers in 1920. And the word robot means basically slave. So it means forced labor. So the point in the play, you had, I don't remember the name, but some company building universal robots, so Robotica, in Slavic, and they were not mechanical, they were organic. So basically like replicants in Alien or Blade Runner. And everything went fine, and they were working happily for humankind until, well, they started a revolution and they destroyed everything and everybody. So that wasn't a good start for the term robot. But anyway, well, actually, the concept of robots existed way before the word robot existed. And we can actually go back to as far as we know in history. And there's always been this concept of artificial system where you can put life in or put intelligence. So in antiquity, you can look at the legends and the myth, and you will find like Hephaestus building tables that could walk, or building golems that could help at home. You would have soldiers to protect temples in Egypt. You would have the same protecting the relics of Buddha in India, the same in China and so on. So everywhere, people have always been fascinated with this idea of creating life out of matter, let's say, out of no life. And also at the same time, you had philosophers also in Greece, China, India, and so on, already thinking about describing intelligence in terms of mechanical systems. So it's really as old as humankind. And why were they already thinking that? Well, because you already had engineers that were more or less building robots. And the first robot in history, well, accordingly to some historians at least, is Akita's bird, which was made of wood, in which you would build up steam, and after a while the thing would pop out, and it could fly and flap its wing for a few hundred meters. And so that's supposedly the first robot in history. And you see already the idea behind it, which was to copy what you could see in nature, in an artificial system. You also had kind of the first analog computers. So you have this anti-Kythera device that was found in, I don't remember where exactly, but close to Italy, I think. That was basically the first analog computer that was able to replace humans to predict Olympic Games and also solar eclipse. Surprisingly enough, you also had very modern things like vending machines. So you would put a coin in there and you would get some holy water out of it. And in China, you already had automatons that were trying to mimic humans doing things. So in this case, playing music. That was before Christ. Let's jump in time, and in the Middle Age, well, basically nothing really happened between Antiquity and Middle Age, except that people were able to create more sophisticated automatons, we would call them. So you have the first humanoid robot, supposedly, which is designed by Da Vinci. We don't know if he actually built it, but at least he designed it, and we found the drawings. You had the Vaucanson's duck, which was able to eat grains, to digest them, and to defecate for some reason. And well, once again, you see really the will to copy animals. The writer that I will show you briefly, which was a very sophisticated automaton, as you can guess. It was supposed to write stuff, and it was amazingly sophisticated. So you have more than 6,000 pieces in there. And why I want to show it to you, it's because, so people were buying it to impress other people. Basically, it was a hobby for rich people. There was no real purpose except making something amazing. But that's very interesting because the automaton is programmable. And according to some definitions, this would be the first robot in history because that's an automaton that you can program. Okay, yeah, maybe a few words on the Pascaline. Maybe some of you know that was also an ancestor of the computer at the time. That was able to, so designed by Pascal in France, able to do addition, subtraction, divisions, and multiplications. And he sold quite a lot of them. And now we jump to the modern era where, of course, a lot of things happened, like, you know, the sciences. And yeah, the point is that now the robots start to become useful. And why so? Well, because suddenly you have access to more power with the more energy, more easily usable energy with steam power and electricity with the first and second industrial revolution. So you have complex machines that start to enter factories and start to be really useful. I also like the steam man and electric man that were, well, looking a bit ridiculous, but the point was that they illustrate well the two revolutions. So the point was to replace the horse. It was in the UK, to replace the horse to pull a cart. And so you see steam man, of course, taking advantage of steam power and electric man of electricity. So you see that robots or complex machines enter factories, but they also start to pour in everyday's life. But of course, the real revolution is the birth of what is called the AI in 1956. So you had a lot of, it was an amazing synergy between many different things. You had Shannon theory, so information theory. Shannon described how you can manipulate information and basically how you can describe everything with 0 and 1s. You had work in neuroscience, where people discovered that the brain is actually a huge electrical circuit and neurons are firing all or nothing signals, so basically 0s and 1s. You had Turing, Alan Turing, which is the grandfather of computers, that took advantage of those discoveries and also described how any algorithm can be implemented in a machine. And on the mathematics side, you also had great discoveries in logic, and so they showed that any algorithm can be described in terms of logic. So everything was fitting together well, and so in 1956, people gathered, mathematicians, neuroscientists, economics, physicists, and so on, and they started the field of AI with a motto. I don't know if I can read it here. Yeah, their motto was that every aspect of learning or any other feature of intelligence can in practice be so precisely described that a machine can be made to simulate it. So at the time, they thought that in 20 years the problem would be solved. And we'll see that, of course, that didn't happen, because that was a bit more complicated. So there was a real boom of robots and AI systems at the time. I will only show some of them. You have Electro, the first, well, after Da Vinci, the first actual humanoid robot that was able to walk a bit, so you could command with a vocal signal and it could walk a bit. It could recognize red and green lights. It could smoke. It could blow up balloons, wave its hands and its jaw, I think. You had the first, well, I think I won't show the video, but you had the first robotic arm, which is called Unimate, that entered the factories of General Motors. And so the point was to replace people doing dangerous stuff, like manipulating dangerous material with this arm. And that was quite successful. You have Shaky, which is the first mobile robot, meaning that the computer that is controlling the robot is on the robot while the robot is moving around. And it was able to move in rooms where you had very simple geometric shapes. Yeah, one thing I want to point out is those two. Maybe I will show a video of the first one. So already at the time you had two different approaches to artificial intelligence. So I will skip a bit this. So this is Gray Walter, and he created what is called the gray tortoise. I don't know if you can see well. There is no computer inside. So the whole point is, it's called cybernetics. The point is, can I connect sensors to motors with some wires, a bit like the brain does, and can I create behavior out of it without explicit computation, without really a computer inside? And so what you see there is, well, this so-called tortoise that is either avoiding light, because it has light sensors on the left and the right, or going toward light. And what is interesting is that you can basically summarize the brain of this robot by with two wires. So how do you connect the sensor to the two wheels? So what is interesting is the brain is extremely simple, but because the environment is complex, you have the emergence of a complex behavior. Yeah, and they can dance also. So that's one approach, basically thinking that the brain is not necessarily a computer, but it's more a connection between sensors and motors. And the other approach was completely the opposite, which was, some researchers decided that the most interesting stuff is very high-level intelligence of humans. So for instance, play chess. That was the ultimate challenge. Are we able to play chess? And so those people would, instead of behaving in the real world, they would forget about the body, forget about the robot, go to pure AI and pure artificial worlds where you would be able to manipulate symbols. And Short Glue is one example of that. So you could stack cubes with a completely disembodied system. And actually that was pretty successful, and that's what led to the beating of Kasparov with Deep Blue in 1986. So that was great, but that's later that things went bad. And I also wanted to point it out because that might be interesting for you. The first robot on the moon by the Russians, that was called Lunokhod 1 in 1960. Now, I said that things went a bit bad. They are called the AI winter. So, as I was saying, when the field was created, people were thinking that in 20 years the problem would be solved. And, well, that wasn't the case. And so at the time you could hear people, so big names in the field really saying that in 20 years things would be solved, or in 8 years we would have a general intelligence like human being. But years passed and there were not so much results. So the results were really in toy worlds like this, but there was no real application in the real world, or chess that you can describe as a symbolic world, which is not really the real world. And so a lot of people stopped funding AI, and that was well, quite a bad time for AI. It almost disappeared. And right now, actually, some researchers are worried because we have once again a new buzz, and maybe we are facing a third winter AI. We'll see in the next few years. But research continued, and well, the winter AI were about AI and not about robotics, because while robots were quite successful, you had a lot of robots entering factories, and they didn't really care about the intelligence of the robot because the robot was manipulating things. The winter was really for AI. But the research continued, and in the 80s you had some great success with what is called expert system. So instead of trying to solve intelligence in general, people started to focus on some very specific domains where you need experts. So let's say medicine. And so the point would be to take one physician or many physicians and try to collect all their knowledge, and you transcribe that, sorry, in terms of logic in your system. So that would be if you cough, you have the flu, something like that. If, then, and you put hundreds, thousands of them in a database, or in a knowledge base, and then you build an inference engine that is able to look at those rules. And if you give some input, I cough, I'm crying, I don't know, something that will tell you more or less what you are supposed to do according to this knowledge. So that was quite successful in the 80s, and that made a lot of money. On the other hand, you had the connectionist approach that I was describing, so having wires between sensors and motors. That also knew kind of a breakthrough thanks to the invention of backpropagation, which is an algorithm that is able to change your network in order for it to make what you want it to do. So basically, Gray Walter, the tortoise, he was designing let's say the weight of the connection by hand. Now with backpropagation, we have a way to make the system learn what you want it to do. I will go back on that later. And you also had a very strong critique of the disembodied symbolic AI at the time, and you had many researchers, and especially Professor Brooks, that was building this kind of robot, that was saying, okay, stop, we don't know what we are doing. Human intelligence is way too complex, it's way too symbolic, too abstract, too high level. Let's go back to very simple stuff. Can we build an insect? And people realized that it was already too difficult for them. But his point was that instead of having this very disembodied world where you do reasoning, let's go back to actual interaction with the environment. And that was also a big boom in the field. So where are we today? Well, you already have quite a lot of robots around you, actually. So as I was saying, in industry you have a lot. So robotic arms, so what is called industrial robots, are I think there are more than 20 millions in factories in the world. Maybe I'm wrong with the number, but something like that. You also have more recently like this robot that you can find in Amazon, and that's why things go so fast with Amazon. It's because robots are doing most of the work. You also have robots that are entering the fields, so milking your cows or doing I don't know what. That's the main part of robotics today, I would say. So not that you don't need a big intelligence to achieve those tasks. Another field which is quite big is medical robotics. So I guess you've already seen that in the news. And more recently, you also have exoskeletons that can help people with disabilities. I go fast because there are many things. So more recently, in the last, let's say, decade, you see what is called service robotics. So if you go in China, you can have a robotic waiter or waitress. This one is supposed to deliver things at home. This one is lowering your moan. Who does know this one? Probably some of you, right? That's Roomba. That's the most sold robot in the world. So it's a vacuum cleaner, automatic vacuum cleaner. This one that I've seen actually in California is well managing or welcoming you when you get into an hotel. That was quite surprising, but it works okay. And you also have some robots guiding you in museum, for instance. So this is called service robotics. You also have social robots. That's more than what we build at SoftBank Robotics. So this is Pepper, our robot. And then you have a funny spectrum between robots and devices like smartphones, because you have a lot of technologies that were developed for robotics that are now into Google Home or Google, no, how is it called? Amazon Alexa, something like that?
Echo.
Yeah, Echo, right. Echo is Google. Well, anyway. So your smartphones, you also have, this one is Jibo, that is supposed to help you do stuff at home and be nice. You have a lot of AI technology in Siri, in Android, and so on. You have Watson, that's played in I don't remember the title, but it's a game, TV, Jeopardy. Yeah, exactly, Jeopardy in the UK, I think. But now it's not only a game; it's also helping physicians with diagnosis. You have telepresence robots, and you have a lot of AI features in Facebook. Educational robots and toy robots. Well, I won't go too much into details. You have now a big boom with drones. You have funny things to play around if you're a child. Autonomous cars and autonomous trucks. That's quite buzzy right now. I think they are not ready yet, but maybe in the next 10 years. Military and space robots. So I guess I don't have to tell you about those ones. But you also have military to defuse mines or to carry very heavy load or to have very sneaky drones around. And research platforms. So there are many of them. I only put 6 to show that they have many different shapes and many different abilities. All right. So maybe I will show some videos of what's the best you can do today. But what is really impressive is that they look very natural in the way they move. So I won't show the whole video, but that's quite nice. I think at some point, so it can also use an arm on top of the robot. So once again, someone is actually remotely controlling the robot. Yeah, I just wanted to show this one because they like to play tricks and to show that the robot is quite robust. That's good that you laugh because people see that and they say, "Oh, that's so sad." And people actually complain, and Boston Dynamics receive a lot of complaints because they are mean to robots. This one is even more impressive when you're in the field. That's Atlas. That's a humanoid robot. So this is starting to be scary. Once again, you have someone that is actually remotely controlled, and the robot, it's more or less scripted, so the robot knows in advance where the obstacles are. So they are the best today, definitely. I just want to show the real world. So after Fukushima, the Japanese were quite disappointed because they have seen Asimo playing the flute, running, playing tennis for years. And they were surprised that Asimo couldn't help in the Fukushima accident. So the DARPA created the DARPA challenge, where they designed a lot of different tasks, well, a lot, 5, I think. And different teams around the world were supposed to compete and see who could do it the best. So the robot is, let's say, half autonomous there. So you still have someone behind the keyboard that gives the goal to the robot, like goes there or turn this valve and so on. So you see that in the real world, things are not so fancy. It's very slow. And if I'm really mean, I will show you the failures, which were more than the successes, actually. So this is a compilation of the failures. So most of the robots, they failed, basically. And only, I think, a single team was able to almost go through the 5 tasks. So you had to drive a car, to go out of the car, to go through a door, turn a valve, pierce something in the wall, and climb upstairs. I think this. No, that's not this one. One is my favorite. So this is on the floor. You see the robot that was doing, the salto. So.
Does it also have to tolerate some radiation, like electronic? Does it have some limit to tolerate radiation also, or it didn't have this requirement?
Radiation?
Yeah.
I have no idea. I couldn't say. So you see the limits, because the robot thinks it's actually touching the valve, but it's 1 meter to the left. So I think this one is my favorite. Okay. So you see that despite what you could see on the news or on internet, the reality is way less impressive than you can think. So now I will dive a bit more into why it's less impressive and why it's an extremely difficult task to do, to build a robot. So, how long here? Okay. I will try to not go too much into details, but I have to dive a bit into what a robot is. By the way, if you have questions, you can ask them freely, because I'll try to be clear, but maybe I'm not. Well, the robot is a complicated thing. On the one hand, you have the physical body of the robot, which is called the hardware. That's the part that is, of course, interacting with the environment, so it's physically there. And the body has sensors, and it also has motors. And on the other hand, you have the software, which is basically the computer. And the computer itself is hardware, but what the computer is doing is software. And we will see later that in order to do stuff, to interact with the environment, the computer, the software needs to have some kind of model of, what's happening out there. Because the computer, the software, is not directly interacting with the environment. It's only interacting through data sent by the sensors and sending data to the motors. All right, so when you want to build a robot, the first task is to describe the task, because it's a very task-oriented problem. So you will have, there's no universal solution. When you face a problem and you want to build a robot, you need to start from scratch, basically, because the hardware, both the hardware and the software needs to be adapted to the task. And once you have your hardware and your software, basically the way people do it traditionally is through a cycle of perception, decision, action. So perception is the environment is generating sensations through the sensors. Decision is you take the sensor data and you try to build a model of the environment. What is the environment? and then you look at your goal and you decide what to do with this model of the environment, and then you send your actions and you actually act in the world, and you loop again and again and again. That's why also the robots are so slow. It's because you have this loop and you have to go through. The hardware part, I won't go too much into details because that's not the most interesting part. But you have a lot of mechanical parts, a lot of different motors, hydraulic, electronic, pneumatic, and you have a lot of sensors. So you need to know where the motors are. You can have cameras, you can have touch sensors, you can have a distance sensor like ultrasound and infrared. LiDAR, it's well, basically a 3D camera that is telling you what's the distance of each pixel. And so on and so on. So a lot of things. Gyroscope to know your orientation. So that was the hardware. Now let's start to dive a bit into the software, and that's where we start to have difficulties. The first thing you need to do is to have some kind of knowledge about your own body. So you build the hardware, and now you need to give this knowledge to the software. So the first part is what is called building a kinematic and dynamic model, which is this kind of thing. So you describe mathematically what is the structure of your body, or the robot's body. And actually you have something like that in your brain. So if you close your eyes and you shut down all your sensors and you move around, you have some kind of idea of where your arm is and your hand is, for instance. So in practice, it's not so funny because you get these kind of huge matrices. So this one is only for a 2D or 2-segment arm, so moving in the plane like this, and you see already the kind of funny matrices that you get to describe where the things are moving and inertia and so on. So it's not the most funny part, but it's necessary. So you build it and you put it in your computer. And the second part is to control it. So you know where your motors are and you know what are your limbs and so on. Now you need to control it. And surprisingly enough, that's very difficult to do. Because you cannot just simply say to your motor, please go to 20 degrees. That doesn't work like that. You will send a signal, which is a voltage, and your motor will do something and will end up in 15 degrees, for instance, and you have no idea. And so what people do is they add a sensor at the end where the motor is, and so you send 20, it gives you 15. You look at the sensor, you see the error it makes, and so you try to compensate for it, and that's called closed loop control. So you go through this process and you can end up being very precise. And once again, that's something that your brain does. So if you go into an elevator, you look at the buttons, you close your eyes and you try to touch the button, and you will, in average, you will have a 2 or 3 centimeters error. But if you open your eyes, your brain is constantly tracking your finger and compensating for the error you do. Yeah, I didn't say why you have error. Well, first, your model is not perfect. I mean, it's mathematically perfect, but your robot is not. You have friction, you have gravity that is pulling you down, and so on. So you have a lot of errors in your system, and you need to compensate for them. I will just show you the kind of things you can end up with. Let's say this one. So just having a model of your body and a controller, you can get up to this kind of thing. So notice that the robot is in a cage because it's very dangerous. It has no idea of the environment that is around. If you put your head inside, well, don't do it. But so it's completely blind. There's basically almost no sensor, only the sensor on the motors to know where your controller has to go. But you can go really fast and really well. So it's a whole field of research to try to control those dynamical systems. And you can do very interesting things. For Parkinson patients, for instance, so people created this spoon. So without the spoon, the person cannot eat, and the spoon can compensate actually for the vibration, which is seen as an error for the controller, and the controller compensates for it. So that was the easy part. Now, so the easy part was to model the body. That was easy because you are building the body and the body is always the same. Now the really difficult part, and that's where the problem is to model the environment. So you can see a funny comics there, which is actually related to a real event. But let's say you want to ask your roboticist to, let's say when you take a picture, you want to know the GPS position and you want to know if you're in a national park. That's easy to do. Now, if you want to detect if it's a picture of a bird that you take, you will need 5 years and a full team of researchers. That's actually more than 5 years. But so just to illustrate the very counterintuitive fact that perceiving the environment is way more difficult than things we could think are difficult. So you can look at that to try to understand why it's so difficult. When you see this picture, I guess you see a duck, all of you, and you don't need to make any effort to perceive a duck. It's natural and you see it. What the robot is seeing is this, numbers. Now the gap between those two, we don't really know how to bridge it. This is very difficult, and the combinatorics of the problem is really huge. What that means is you could say let's take 10 or 20 years, and we will look at all the possible images we can see in the world, and we will try to store them, make a huge table of what we can see in the world, and that's done. The problem is that if you take a 600 pixel image, binary image, so each pixel can only be black and white. 600 is very low resolution. Some physicists computed that given the theoretical upper limit of the computational power of matter since the beginning of the history of the universe, so since the Big Bang, you wouldn't have enough time to go through all the images of a 600 binary image. So the whole history of the universe, and if you could build a computer that is the size of the universe, you wouldn't have enough computational power to solve this problem that seems really simple. So that's really a difficult problem, and we don't know how to do it. It's sometimes called the Moravec paradox, which is that basically we know how to play chess, and playing chess seems like a very high-level and difficult intelligent problem. Actually, the real problem is to do everything else. So trying to control your body and move in the world. So how do people do things? Well, they try to simplify the problem. So instead of modeling the whole environment, you try to simplify the problem. Let's say in your task, you have to track or to move towards colored balls. Well, you will take your picture and you will filter the color of the pixels, and you will try to look at blobs of pixels of each color. And you can take the center of the blob and you will say, this is the position of my ball. So if everything is fine, so if all the assumptions you make about the simplicity of the model are correct, that will work. The problem is that, let's say you want to track the red ball and you have something red in the background. Suddenly you will have two blobs of red pixels and you take the center and you're completely off. And your robot has no idea because it doesn't really see the environment. It only sees the center of what you think is the ball. So very complex. People to do computer vision often look at the edges in the image. They look at lines. So all those is called features. So there are things that are simple, that the engineer can design, can look into the image, and that they can also manipulate because they semantically know what a line is, for instance. Corner of the eyes when you want to, or the mouth when you want to detect a face. The shape of a specific letter in a wave sound and so on. And this is a LiDAR. So I was describing a LiDAR that is throwing lasers, and you have the 3D position of each pixel. That's the kind of image you get. So when you look at that, you as human definitely see a car and a different car and a different car and a building. The robot is only seeing points. And so you need a human to describe, okay, if you see this kind of points at this level, let's assume it is a car. And if you see two moving stuff like that, let's assume those are legs of a human. All right, so let's say you have a good model, so you can extract features that are enough to solve your task. The next part of building a robot is to do planning. So you know where you are, you know where you want to be, and you know you have some idea of what the environment is in between, so if you have obstacles. Now you have to do planning, which is how do I go from where I am to where I want to go. This is once again a whole field of research. I won't dive into it, but just know that it's very difficult once again, because the robot is not living in the 3D world like we do. So it's not conceiving the trajectories the same way, because for the robot, the space is the motor space, or sometimes called the joint space, which is the position of its motor. So if the robot has 20 motors, the space it is living in is not 3D, it's 20D. And so the way to do planning, so to find a trajectory in there, is to, well, if you identify obstacles, you project them in this motor space. So they take a really weird shape in this 20D space. And then you have many techniques to try to go from somewhere to somewhere. I won't go into details. Oh yeah, that's supposed to be a GIF, but that won't work because it's a PDF anyway. So those are just showing that you can go from somewhere to somewhere. That's not the most difficult part, I would say, if the environment is not dynamic. So if your obstacles are fixed, you can think about it, about what you have to do, and then you design a trajectory and you find it. One thing that is interesting is that usually your robot has enough degrees of freedom so it can move freely enough that you have an infinity of trajectories between one point and one point. If I want to go from there to there, I can do this, or I can do this, or I can do this. And so when you do planning, you also try to select the most optimal trajectory. And optimal can be many different criterions. It can be energy consumption, it can be speed, and it can be many things. Yes, just a word about reactive systems. So I described building a model of the world or estimating a model of the world. I described planning. Sometimes you can go with an easy solution, and that's what the Roomba did, for instance. So sometimes the task is so simple and your robot is robust enough that you can skip that, and you can build a very simplistic system. So let's say you want to go towards a red ball, and you have a Roomba. So let's say you have two wheels, left wheel and right wheel. Well, an easy way to do it is you split your screen or your image in half, and you count the number of red pixels on the left, the number of red pixels on the right. And if you have the same value, you go straight. If you have more pixels on the left, you go left. And so you will move your right wheel more than the left, and so on. And so your robot will naturally move toward the ball. That's a bit the idea of the gray Walters turtle. And as I was saying, it's actually applied. So the robot that is sold the most in the world is applying this kind of stuff. So it doesn't have any real model of your room or of your home. It's just randomly, not really randomly, but moving in some reactive way when it sees a wall, for instance. All right. So that's what people did between the 50s and let's say the 90s. But then came machine learning. And that's what is, well, the most interesting, I guess, in AI today. So the concept is not new, but we really know a big boom since 9 years. So what's the idea? Instead of modeling the world, so designing features and trying to extract features, which is very difficult and very tedious, why not letting the robot learn about the environment? So you feed it data and it will learn what the environment is. That's an idea that Alan Turing already had in the 50s, so that's a very old idea. Here you see more or less the idea. You need a teacher and you need data. So let's say this was the image of the duck. You feed the learning algorithm with the numbers corresponding to the image of the duck, and you say that's a duck. And you run your algorithm, and if you run it well enough, the next time you show this, it will say it's a duck. That sounds amazing, but that's actually very difficult. Once again, a whole field. I will just try to give you the gist of it. To do machine learning, you need, as I was saying, data. So you need data, for instance, from a camera, but you also need data from a human that is telling you it's a duck, or it's a cat, or it's a dog, or it's a car, or it's someone saying yeah, hello, because it's not necessarily an image. You need a model. You need a performance measure, which is telling you how much your algorithm is doing. So if you feed an image of a duck and it says it's a cat, you say that's bad. If it says it's a duck, you say that's good. And you need an algorithm to change the model when it says it's a dog, in order for it to say it's a duck. So I will give you really the most simplistic example, which is, I guess you've done it in high school, which is linear regression. And maybe you do it on a daily basis, I don't know. That's the most simplest machine learning algorithm. The input is X, the output is Y. So let's say X is your image, Y is the equivalent of saying duck. And you get data points like this. And you see they are along a line. The model here is a line. So the model is two numbers, A and B. A is the slope and B is the bias of your line. The performance measure is the error you make between the line that you think it is and the actual line. So for each X, you can compute the error between the data point you have and your line. And the algorithm that you use to optimize this could be, because you have different ways to do it, but could be gradient descent. So what it is. There you see the space of the data, and there you see the space of the model. So this is A, this is B. All right, and what you see there is the function, it's the performance measure of, so the error that you make when you select this A and this B. So when you start, your line is completely flat because A is 0 and B is 0. And your error is pretty average. And what gradient descent does is it looks at this function. It actually doesn't have access to the whole function, but let's say it does, and tries to move downhill, so make less error. And so the next time it will change A and B, so in order that to get your green line, and it will change again, and you get the purple line, and it change again, and so on, until you reach the bottom of the valley there, and you get a perfect model. And so you can now fit your data, so every time you feed a picture of a duck, you will say duck. That's basically machine learning in a very simple way. The thing is that, of course, it can grow way more complex. So that will be fairly quick. Maybe I will pause. This is the real function you want to approximate. So this one is not a line anymore. It's something a bit bumpy. This is the data you get. So the input space is 2D this time, right? And the output space is 1D. So this is 2 pixels of the image of a duck, for instance, and this is saying duck or cat. And what you see there is the model that is learning, according to this data, what it thinks the function is. And you get something really nice. And there you see the error that is going down. So that's the limit of what we can represent. Because after that we go into way more higher dimension, and so beyond 3D I cannot represent it, but you can apply it to way higher dimensional problems. So you can, you can feed your model, instead of having 1D, you could have 600D, like the 600 pixel image that you want, and the output would be the class of what you see. So about the model, the most, or let's say the favorite model of the researchers today in AI is the neural network. So very simply, a neuron, it's loosely inspired by biological neurons, but they are quite different in practice. But let's say that's a very simplistic model. So your neuron is connected to other neurons through connections that you could see similar as dendrites. It's just summing the excitations of those previous neurons, applying a sum nonlinear function, nothing fancy, and just generating an excitation. So That's looking at other neurons and trying to propagate the message. And the neural network is just a combination of many of those neurons. And they are organized in different layers. You get the input there. That's where you would put, for instance, the excitation of your pixels of the image. And then the excitation is propagated to a different layer and a different layer, and then to the output. And each layer is actually transforming the data, let's say. So you get your pixel, and then you get something a bit different and a bit different. And based on this something a bit different, the last neuron is supposed to tell you what it is. Yeah, I will stop there. Now, there is neural network and there is deep neural network. There is absolutely no difference. The deep means that you have more than one layer there. That's all. But in practice, in the last few years, let's say 9 years, well, there's a big boom because suddenly you, thanks to internet and big data, you have access to a lot of images, for instance, on Google. And you also have big databases of people telling you this is a cat and this is a dog. And you also have new GPUs that are able to run really efficiently this kind of big network with many, many, many different layers. So now the networks are growing very big. And why do we do so? Well, the bigger your network, the more complex the function you can approximate. So if you remember the bumpy function, it was still fairly simple. But the more layer you have, the more bumpy and the more transformation you can apply on your function. So as an ID, there on the top, oh, it's a bit fuzzy on the screen, but you see, so you have an ID of, that's a bit tricky to describe. Let's say you have a deep network, so you can feed it 2 inputs, and you have many different layers, and you get some output. And this is describing in your 2D input space the number of different decisions that the network can do. So each small colored piece there is the network telling you it's something different. So this would be a car, this would be a plane, this would be, I don't know, someone saying hello. So you see that the function can grow very complex. And that's why people try to have, are using very big networks. The problem is the bigger your network, the more data you need to actually do the gradient descent, so to learn the function. Because those huge networks, they actually have billions of parameters. So it's like you are approximating a function with billions of parameters. And you need a lot of data to tweak the different connections between your neurons to get something meaningful. So recently, one of the fathers of deep learning proposed to call it now differential programming because it's moving really far from the original idea of neural network. And now people, what they do is, well, they have some function, so they have a program in mind, but they don't want to program it. And so they get inputs, and they say what the output of the program should be, and they just apply this kind of big network to try to learn the program between the input and the output. And so it's called differential because you are doing gradient descent, so little by little you change your program inside the network to do what you want it to do. Well, with those deep networks, people have pretty amazing results. So this is the error rate of so recognizing different images in a huge database which is called ImageNet. So ImageNet was proposed in 2012, I think. It's 14 million images that were hand-labeled by humans. So humans went through 14 million images saying, this is a boat, this is a cat, this is I don't know what. And you have 20,000 different classes, so things that you can recognize. So that's a huge work. And you need this amount of data to feed a deep network for it to be able to recognize those different categories. And through the years, since 2012, you see that this is on this database, not in general, not in real life, but on this database, this is the error rate of humans. And you see that the machine learning systems are now better on those databases. This is this kind of system that actually processes your images when you upload them on Facebook. Well, actually not in Europe, but anywhere else in the world, and that's happening. You have the same very recently for audio, so processing speech, with an additional trick to the network. So the way I described it, you have input, layer, 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 output. The thing is that it's you don't have any memory of idea of time in this kind of network. And so what people do is they use a recurrent connection there. So let's say in the A there you have a lot of neurons. This is your input, this is your output. And people add a connection like this. It's simply representing the fact that the neurons, they take input from, well, the image you give, but also from their previous state. So that means that now in time you can, let's say, give the different points in a wave sound. So this would be the first point, second point, third point, and so on. And what your neuron was thinking for the previous point is propagated to the current point. And so you can now process sequences in time. That's the gist of it. I won't go into details. And so very recently, once again on specific databases, those machine learning algorithms are better than humans to recognize speech. That's the kind of system that is used in Google Translate, in Android. So the voice that is generated, so the voice of your Google Assistant is generated by such a network. It's also a different network that is processing the speech when you say something to Google Assistant or to Siri. So that's already there. Now, as I was saying, there's a huge boom of applications right now with deep learning. I will show some of them maybe. So this one is interesting for autonomous cars. That's the kind of thing you can do. Maybe, yeah. So this is real time. This is the camera you could have in your car, and it's recognizing cars and people, and it's also able to track them, traffic light. So this one is not so good because it's the quality is decreased in order for it to run live or real time, and you can have better results, but not very fast. So that's something that was completely impossible to do 5 years ago, or even 4 years ago. And so that's why you have a big boom, because deep learning is making new things possible. You have other examples. You can generate automatically a description of an image. So you upload an image. I'm sorry you can't read it, but the network, recurrent network, is able to describe the image. So a girl is jumping in a park, something like that. Someone is playing the guitar. As I was saying, you can translate text between two different languages. That's what Google Translate is using. You can colorize old pictures. You can, well, we don't see the difference there, but this is a noisy image, and your network can remove the noise. And that's a bit the same here. I mean, it's supposed to be a GIF, but we don't see it. So in all those applications, there are very neat ideas by engineers for domains where you can find a lot of data. So let's say this. Actually, what they did is that they took all pictures, but colored ones. They made it all the pictures gray, and suddenly you have the gray picture as input and the colored pictures are as output, and you have a lot of them. You can train the network, and now when you give a gray image, it will generate a colored image. More recently, you have what is called generative networks. It's the same idea. It's still deep learning, but it's with a small subtlety, which is you don't necessarily give or tell the network what the output should be, but you feed it with a lot of data, let's say of faces, a lot of data of faces, and you ask it to generate something like the data it's in, and it will generate a face. So let's say As you will see, that's not perfect. So this is not at the application level yet. This is still research. But this is a kind, so they fed the network with a lot of celebrity images, faces. And this is faces that are generated, so artificial faces generated by the network. So they look quite good. If we look at yeah, this is funny because, well, the way it's done is you can continuously move into the let's say the space of the network, and so you can continuously change faces into others. And those are all fakes. They are not actual faces. You can also generate a fake Obama. So not Obama, but only the lips. So sorry, there's no sound, but the basic idea is that they take a speech, not necessarily Obama speaking, but someone speaking, and they can generate the lip motion of Obama speaking. So that's a bit concerning because maybe in 5 years, the video you will see about your president in the news is fake. So there they took the speech from Obama there, and they make Obama speech, this speech, in this video. So that's called, well, this family of algorithm is called deep fake. You can also do, how is it called? Style transfer. So you can feed the network with a lot of database of landscape, let's say, and you feed it also with a lot of painting, not necessarily a lot, with some paintings of a very specific painter with a specific style. And you can ask the network to reproduce this one using this style, and you get, well, paintings. You can do that with Picasso, so it's an image of Picasso, you feed a painting of Picasso, and you get Picasso painting Picasso. This one is the most recent. It's fairly impressive. I don't have the video, but you can feed a lot of images of horses, a lot of images of zebra. And now if you feed a video of a horse, it will transform it into a zebra. And maybe I will show the last one on the top left. Yes. So there you will see, on the top right, you see the actual video frames that are fed to the network. And the network is trying to continuously generate an image with a higher frame rate. So you see that it's fairly slow, and the network is generating something that is smooth, and so it's kind of simulating how things move in space. Well, it could have a lot of applications, like playing video games on internet. You don't have to feed all the data. You can just feed some of them, and the network can interpolate. So many different applications. So those are great. Those are the kind of things that you can find in your smartphone, let's say. But we were talking about robotics, and in robotics, we don't care about the lips of Obama. We want the robot to do something in the world. So we want the network to generate an action. And while deep learning also can do that, and it's called, the framework is called deep reinforcement learning. The idea is you don't want, because you don't know, you don't want to tell the system what should be the action it does. But what you can do is tell the system when it does something great. So let's say you want to balance a pendulum like this. You will create a network, and you will, through trial and error, it will try to do stuff. And there you want the pendulum to be in the upper position, upper equilibrium. And so when it spends its time like this, you say that's bad. And so we try to correct it. And here you see the number of trials it does. And little by little, it will learn to balance the pendulum. And once it's up there, you say, that's good. And so you give it a reward. And in the end, you get this behavior, which is almost perfect. So there, the output of the network is an action. And you can go pretty far with this approach. And you can do this. So notice that it's in simulation because you need to make a lot of trial and error, a lot of trial and error. And so you cannot do that in the real world, but you can do that in a simulation with a powerful computer. And so every time it fails, you say that's bad. Every time it goes, so the further it goes, the better, and the more reward you give. I think I will go to the humanoid one, which is way funnier. So the whole behavior of the robot has been generated by a network, and the only feedback you give it is, are you moving forward? And the more forward it goes, the better. So it has no notion of aesthetics, so it doesn't care about the dance. Once again, that's very impressive. That's something you couldn't do 5 years ago. So this is this kind of approach that beat humans at AlphaGo recently. I guess you saw that in the news. I think it was 2016 in March. So basically, with this kind of approach, you can beat any human at any video game. So it has been done in Atari. It has been done in Dota 2 for people that play video games. Very recently, it has been done at chess. So the same algorithm that beat humans at Go was applied to chess, and it beat all humans, and it beat also all previous algorithms. And some attempts have been made to kind of reproduce this trial and error process with the real robots. But as I was saying, it's very difficult because you need a lot of examples. It's difficult to get in the real world. Finally, a last approach that is maybe more interesting to you because you're interested in natural selection and evolution, while we copy you and we do artificial selection and artificial evolution. While the process, so it's loosely inspired from biology, instead of having one network, so like this one, it's one network that is generating a behavior, and you by gradient descent, once again, little by little, you change the behavior. This one, you have many different networks generating behaviors in parallel, and you select the best of them. And you mix them, and you create a new generation, and you test again, and you select the best, and you mix them, and so on. And you can get pretty amazing results with that. So this is an antenna that was designed this way by for NASA. And the design is really weird, but actually it's way more efficient than what an engineer could have built because of its weirdness. And there I will show you an example of something we did at SoftBank. So we let Pepper discover how to play Bill Bokeh. So we give one initial demonstration because if you are using a real robot. So if you try forever, I mean, you will spend 20 years before you do something that is close to what you would like to get. So you try to initiate a first motion, but it doesn't need to be successful. And then you let robot try and try again, and you see the number of trials there. So what is great is that it doesn't get bored. Almost. So it did it. And the best thing is that after, when you you save this behavior, and then you test it again and again, and you can play perfect bilboquet. Well, believe me, I won't go through that, but it does 15 in a row, perfect rows. And so this is through artificial evolution. So each trial that you saw was basically a different brain, and you select the best brain. Okay, so that was how to build a robot and what we can do today and our AI systems. Now let's dive a bit more. I will try to be fast in research and the future. Very quick. Of course, you have a lot of hardware improvement, but I won't go into details. You have a lot of work on batteries because that's a big limitation. People are also trying to make. That was supposed to be a picture of Baymax. If you've seen, I don't remember the title of the movie, but a big fluffy robot. People are trying to build safer robots by making them soft. So that's the kind of things you could say. This is a better LiDAR. So a lot of things are happening there. But the most interesting about research is the AI. So the first part, let's say, of the community in research in robotics is trying to overcome very strong limitations of the current approaches. So the first one that I pointed out already is that in order to apply deep learning to a problem, you need to collect a huge amount of data. So to recognize cats and cars, you need 20,000 categories. You need 14 million images that a human went through. So that's a real problem, and people are trying to, of course, overcome that. The parkour guy that you saw, in order to get this kind of behavior in simulation, not in real life, in simulation you need 6,400 CPU hours, which is a lot. And for the algorithm Alpha 0 beating humans at chess, it was done in 4 hours because they did it in parallel on many computers. But actually, if you sum up the computation that was done, if it was a single agent, that would take more than 3 years to learn to play chess. So the result is impressive, but you need a lot of computation and a lot of data. And that's a limitation for going from simulation to real world. Now, that was a fairly trivial limitation, I would say. Now, the 3 others are more profound. The first one is that, once again, as I was saying, those robots and those AI systems, they rely a lot on humans. So you need a human to describe the kind of model that you will put. So basically describe the architecture of your network, and you need to trick it to be able to do what you want to do. You need a human to collect data, the correct data, and to pre-process it so that they look nice, let's say. You also need humans to label the data. So the human is still everywhere. Here, if you remember the horse and the zebra, if you feed an image that doesn't fit the data that the machine learning system learned, so that's a horse, yes, but you have pudding on it, and the output of your system will be a zebra with a zebra pudding on it, because the network was trained with only horses. It doesn't know what a human is, and if you feed the wrong data, it will do something weird. So you still need a human in the loop. Now, this is probably the strongest limitation, which is that those systems, they look very impressive, but they actually have a very weak data or understanding of what the environment is. So the Putin zebra was already an example, but well, I could give you many things. So, for instance, this is the UK police. They were trying to apply a deep learning system to recognize pornography on the internet, and the system thinks that dunes are pornography because, you know, that looks a bit like it. This is how's it called? Wall breaker. So you can train a deep reinforcement learning system to play wall breaker way better than humans do. Now, if you change the color of the palette, or if you add a small block there, or you change the color of the blocks, the AI has absolutely no idea what to do. So it didn't really extract the fact that it's playing a game with a palette, that it's moving, and you have a ball bouncing on walls and blocks and so on. It doesn't really understand that. It was trained in a fixed setting, and it can do the best in this fixed setting. Now you change a bit the system, and it's completely broken, so it's very brittle. When they do errors, they do very absurd errors. So this one is an example of feeding an image and generating a text, and it's saying that it's a refrigerator full of food. And there is absolutely no relation with what you're seeing on the image. So the errors makes absolutely no sense. This one is probably the most concerning. You feed that to your network, it says it's a panda. You add a little bit of noise, which is completely invisible to humans, and now it says it's a gibbon. And you can do the same and say it's a telephone or say it's a car. It's called adversarial examples. It's a bit difficult to explain because it's very technical, but all the AI systems are susceptible to this kind of mistake just by the way they are constructed, and we don't know how to go around them. And this is a video of well, I guess I won't show it, but it's a turtle that was built in order to be recognized as a rifle any way you look at it. So the system that was recognizing people and cars in the street, if you show this turtle to the system, it will say it's a rifle. That's very concerning because you can change stop signs into green lights. So if you just add small stickers in the image on the road in the real world, and the camera in your autonomous car will think it's a green light. So be careful. That's why autonomous cars are not out yet, because you have those kinds of problems. Another example of the non-understanding, really, or weak understanding of the world is you can recognize images of cats, but then if you show a drawing, it has absolutely no idea what it is. But if you show this, which is a scattering of different parts of the cat, it will say, yeah, that's a cat, definitely. And it doesn't see the difference. And you can see the difference with a human child that can see a giraffe in a book. And when it goes to the zoo, it recognizes the giraffe. So it goes from a drawing to the drawing to a 3D animal with no problem. So there's something really different there. And finally, the last limitation is that those systems, they have no autonomy. So they are very specialized. They are designed to do one task, and they won't do anything else. So let's say you want to generate the lips of Obama. Of course, you won't generate the frames of a video, or you won't recognize cats. Those are completely different systems. And so we don't have an integrated solution that you can put in the world and it will learn to do stuff around. So I like to show two examples, maybe. This one is a dog versus a dog, but an artificial one. So the artificial one, that's Boston Dynamics once again, is remotely controlled by a human. And you see the difference between the artificial system and the actual biological system. And you see how the real dog is a completely integrated system. So it doesn't only move like the other one is doing. So first it moves autonomously, but it's also scared. It's also communicating with humans around. And the dog, it never saw this kind of stuff in its life. And it doesn't need 10,000 examples of images of it to recognize it. The first time it sees it as a dangerous animal, and that's done. So we are far from it. And another example that is very interesting in this one. So our system right now, you turn them off, or you don't provide any goal, and they just stand there. So the robot won't do anything. And it's way different from us, because we have intrinsic motivation, and we constantly want to do stuff. And there you see a baby that is discovering that it can stack blocks, and you will see how excited he is, because it's intrinsically rewarding to design new goals and to explore the world, and that's something we don't have at all. Well done. So, briefly, are current systems genuinely intelligent? Well, that depends what you mean by intelligent. What we have today is what we call weak intelligence, which is we are able to solve some very specific problems in an intelligent way, something that looks intelligent. But we don't have what is called general intelligence, which was the goal when the field of AI was created, which was to emulate human intelligence and all the baby behavior and the dog behavior that we saw just before. So being in the world integrated and doing a lot of stuff in an open-ended manner. A good metaphor for it is you see birds, you want to fly, and you build a plane. So yes, you fly, but you do it in a very non-flexible way. So the bird is way more flexible and can do way more different stuff than your plane. And so right now we have planes and we don't have birds. I wanted to put a planet just for you. Right now, so if we look at general intelligence, this is still a completely unexplored planet. Well, not unexplored, but mysterious planet at least. And sometimes people in the field of deep learning describe themselves as alchemists, because we are really in a, well, pre-chemistry time, because we don't know what are the rules. And so we try to understand what is intelligence deeply, in a profound manner, and try to, well, explore that. And, but we don't know yet. We didn't crack the code of what the brain is doing. So not everybody is doing very applied engineering stuff like autonomous cars, and you still have some, well, rather a small part of the community that is trying to deal with a genuine intelligence problem. And in particular, I'm working in what is called developmental robotics. So in a nutshell, the approach is taking inspiration from babies and children, like we saw, and try to identify the minimal mechanisms that you would put in a system for it to grow intelligence. So the metaphor of the crystal is pretty good, because you don't want to build the crystal, you want to find the basic mechanisms that will allow the crystal to grow. So you don't want to build the complex stuff, you want to build the easy stuff and let the intelligence grow. Like the baby explores the world and builds up intelligence. So that means discovering a lot of stuff, discovering the world, of course, but also discovering your own body, also discovering social interaction and language. I will show you some work on discovering your own body that was done in the lab. So this is the Now robot, and you remember that previously I said that in order to move as a robot, you need to describe a model of your motors, your limbs, and so on, and then you need a controller and so on. While we do it another way, we don't give any knowledge a priori to the robot, and we let the robot do what is called motor babbling. This is what babies do. You know, babies, they do weird motion when they are babies, and they're actually discovering how their body is moving when they send motor commands. And so we let this robot do this motor babbling for 15 or 17 minutes there. I will skip ahead. So it's basically a baby robot discovering its body. And in particular, what we want to learn there is specifically learn to control your orientation. So it's like in your inner here, you have some, let's say, gyroscope that tells you what is your orientation regarding, with regard to gravity. This robot has the same, it has a gyroscope, and we want to learn to control this sensation by motor babbling. And so that's done, 17 minutes. And in the end, we ask the robot, so we enter a command line and we ask it to move from left to right. And it can do it in a really weird way, but it does it. So remember, it only trained for 17 minutes, and a baby needs months and months to actually learn to do it in a smooth way. But that's the kind of approach we have. So we want the robot to build its own model of itself, of the environment, other people, and so on. Now, I guess some people know that, right? We also take inspiration from psychology and neuroscience, and in particular, more and more neuroscientists are now describing what the brain is doing in terms of predictive machine. So why is that interesting for roboticists? Basically, they are saying that what you perceive about the world out there, it's not really what your sensors are sensing. It's mostly in your brain. So what perception is comes from within. And your brain is constantly, so it has a model and it's constantly generating hypotheses about what's out there. And this is what you perceive. Now the sensory input coming from your sensors, they are just updating slightly those models and see if it fits with the hypothesis. So that's important for us because the traditional way in robotics is to take the sensory input and try to generate perception out of it. But it seems like the brain is doing something quite different, generating hypotheses constantly. So I don't know if you see what's in those pictures now. You had 2 minutes to look at them. This one in particular.
Dalmatian.
Sorry?
Dalmatian dog.
Yeah, so you can see a dog there. You have the head. You have probably a tree there. So it's a dog in a park. And this one is a neck. So you have to turn your head this way and you see the bottom, the ear, the hair, the shoulder. So, and this one, maybe you know, some people will see it blue, some people will see it white, I think. I see it blue, definitely. Why those? It's just to show you that the sensory input, so what comes up on your retina, is not really what you see. So before you know it's a dog, you see just black and white stuff and there is no content in that. Now that you know it's a dog, you see a dog. And forever, if you see this, you will see it one day. So you have the leg there, the front leg, and the dog is probably drinking. That's okay. Not everybody has to see a dog. So the point is, with the same sensory input, because you updated your inner model, now you see a dog. But it was the same sensory input before. And well, you can spend your evening on it. Do you see the neck? The neck is easier, I guess. This one is the same. So you see blue. So the sensation on your retina is exactly the same. But depending on what your brain hypothesizes as lightning condition, you will see blue or white. And if you're flexible enough with your brain, you can actually switch between them. So that's just an illustration of what you perceive is from within. It's the hypothesis that you have. And so we try to reproduce this in our systems. And I will end up with I will send you the picture later. So the last part is sensory motor contingency theory, which is very difficult to explain, so I will do my best. But the last limit of what we don't know how to do is, can we make robots feel stuff? So when we see blue, I feel something like blue, and when I see red, it's different. Why? And we take inspiration from this theory, which comes from neuroscience and psychology / philosophy, which is claiming in a nutshell that once again the sensory input is not what is important really. What is important is the way you can interact with it. So I can give you a very simple example of a line. So why should you perceive a line as a line? Why do you perceive a line differently from a circle or from a sphere? The reason is not necessarily, so if you look at how the brain does it, well, we don't really know, but the first thing that the brain has access to is, if you look at how the line is projected on your retina, it doesn't have the property of a line. So it's a weird mix of cell and rods, cones and rods in your retina, and depending on where the line is in your field of view, it will be bent, and you still perceive it as a straight line. Why so? And the sensory motor approach tells that it is a line because you have a very specific way of interacting with it. If you look at the line and you move your eye around, you will change your sensor input, right? Except if you move along the line. So if I'm looking at this line, if I move up and down, I will change my sensor input, but not if I move left and right. And this is very peculiar. For the brain, that's very specific. What is a sphere? Well, a sphere is also some kind of sensory-motor invariant. That's something that, why is a sphere different from a cube? Because a sphere, when I move it or when I move around, it doesn't change. And the cube does. But the cube has another kind of invariant, which is if I turn it 90 degrees, it's once again the same. So this is the kind of grounding of the feeling that we try to put in a computer, basically. So the way I told it, it sounds like it only applies to geometry, lines, cube, and sphere. But actually, the sensory-motor contingency theory is the only one that is naturally predicting why we perceive 4 pure colors instead of 3. So we have a trichromatic visual system. And I won't go into details, but this theory is basically the only one that is naturally explaining why we perceive 4 pure. And it has to do with the way, so when I look at the color of this surface, actually when I move around this way, my sensor input changes in a very specific way, which depends on this color. And so color, which looks like it's completely uncorrelated with action, might actually be very linked with our ability to move in the world. So I did my best. That's very difficult to explain. What about the future? I picked this picture because for 2 reasons. First, will robots be sentient and be intelligent and will ask about their own being? But also, will they be a danger for us? Well, I usually don't talk about ethics in my work. I mean, most people that you will hear talking about ethics and the singularity and robots killing you, none of them are in the field. None of them know actually what the algorithms are doing. So that's a concern. So we don't usually really care, but we, of course, think about it. In the short term, definitely you will see more and more robots. So you will see robots in factories more and more. You will see service robots in the streets, in the train station, and so on. You will see more and more deep learning applications, but they will reach a plateau because of the strong limitations that I showed. Now, in the very long term, that's very difficult to say. So will we be able to have general intelligence in a robot? Sorry. First, we don't know, because we don't really know what it is. We cannot really know what the type of intelligence it will be. So we don't know if it will be dangerous or not. But definitely it will have strong consequences for society. So let's say you can build robots that can produce goods and produce energy and can produce other robots. Well, suddenly humans don't need to work anymore. So we will need to completely restructure the way we organize the society. Now, will they reach singularity and destroy us? Impossible to say, I would say, today. But I don't see why they would. So usually humans, we tend to project very negative things in robots because we come from natural selection and we had the will to survive and to fight with each other to survive. The robot will not be the consequence, intelligent system will not be the consequence of natural selection. It will be through a process of human building them. So they have absolutely no reason, a priori, to want to survive and to want to destroy humans in order to survive. Well, I don't have really much to say about it. If you have concerns, pick the first movie. If you don't have concerns, pick the second movie tonight. Yeah, and that's all. Thank you. I don't know if you can hear that.